So now let's talk about why it is so inherently difficult to track what the atmosphere is doing from moment to moment. The density of the Earth's upper atmosphere is constantly changing. And there's two major effects in play and then a whole lot of minor effects. The sun puts out what is known as extreme ultraviolet radiation, or EUV, and as soon as that hits the atmosphere, that produces a heating effect that is nearly instantaneous and drives the local atmospheric density. And then there's also geomagnetic interactions. You have collisions with the atmosphere with charged energetic particles, and these cause a delayed heating effect. And so both of these constantly drive atmospheric variations. The Earth does something different, and the atmosphere follows. The sun does something different, and the atmosphere very quickly follows. Atmospheric fluctuations are going to be distributed both spatially and temporally, and they have both random and cyclic behavior. The most important cycles, and this is a small subset of all of the cycles in play, there are daily diurnal variations. The atmosphere bulges in a direction that lags the direction of the sun. So this instantaneous heating effect has this somewhat delayed reaction. And so around 2 p.m. local time is when you get the most heat. And I think we recognize this from our day-to-day experience because we know that it tends to be the hottest afternoon. There's the solar rotation cycle, and that means that the same solar active regions will come into view of the Earth approximately every 27 days. And it's fairly coincidental. This just happens to be close to a lunar month. That's just how the solar system happens to be. And then finally, there's the overall solar magnetic activity cycle. The sun has an active cycle with a period of approximately 11 years. And this can be tracked by the observed number of sunspots. And so there's a solar maxima and a solar minima, where the sun is the most active and the least active. There are lots and lots of different atmospheric models, and one of the most widely used is known as the US Standard Atmosphere, which was published in 1976. And this is just a single plot from this very long report, which you can grab from the NASA Technical Report Server. And this is showing the temperature profile as a function of the geometric altitude. Here you have the 1% extremes and the min-max monthly measured temperatures, along with a mean atmospheric temperature profile. And you can see that it's not a monotonic relationship. The temperature is going to go back and forth. It's going to drop as you climb to 10 kilometers and then keep steady. And then you pass a cloud deck layer, and then you're going to have this inversion where your temperature climbs briefly. And then after about 50 kilometers, you're going to have a pretty steady drop in temperature and up to the Kármán line. And here you're technically considered to be up in space at about 100 kilometers or so. We've been tracking solar activity for years and years, all the way back to the 1940s. And there's actually a really interesting point about tracking solar activity. The main source of heating is due to UV radiation, but ozone, which is a byproduct of having oxygen in our atmosphere, is an almost ideal UV absorber, which is great for us because ultraviolet is harmful to humans and other biological life on Earth. And so it's great that we have an ozone layer, but that means that we cannot make ultraviolet measurements from the ground. However, the ultraviolet radiation originates from the same layer of the sun as radiation with a wavelength of 10.7 centimeters. And 10.7 centimeters is squarely in the radio band, where the atmosphere is absolutely transparent, and also happens to be where a lot of radar operates. So starting from the 1940s, when radar became a thing, we have been making detailed measurements of the flux at 10.7 centimeters, which is known as F10.7, which is an ideal proxy for what the extreme ultraviolet radiation is doing. We define one solar flux unit as 1 times 10 to the negative 22nd watts per meter squared per hertz, and we report SFUs in this F10.7 band, which tells us basically what the sun is doing to our upper atmosphere. And so you can see here, this is just a plot based on data that I grabbed from this site, which has a lot of historical information. And you can see the various cycles in play here, including that 11-year cycle, which has a minima here and then here. So you can see that we are just now in 2022 coming out of the last solar minimum. We can similarly measure the Earth's geomagnetic activity, because remember, that is the other important perturbing effect on the atmosphere. The Earth's magnetic field also varies temporally and spatially. And unsurprisingly, you fit it with a spherical harmonic model, exactly the same as we do the geopotential. We define a geomagnetic planetary index K sub P that measures worldwide geomagnetic activity. And we can also define a daily planetary amplitude A sub P, both of which are given in units of something called gamma, which is 10 to the negative 9th Teslas, or 10 to the negative 9 kilograms seconds per meter. Once again, all of this data is widely available. And so here is a trace from 1940 to 2010 showing the monthly mean A sub P. And you can see that there's variations in patterns, but also a lot of noise and a lot of chaos and a lot of outliers. Some of these are most likely spurious measurements, but you can see the difficulty of using this data set. You can fit various polynomials or other types of functions to this to try to extrapolate out and make predictions, but that's fraught with peril because of the randomness and the inherent noisiness of these signals. And all of this put together makes it incredibly difficult to predict what the atmosphere is going to be doing from minute to minute or orbit to orbit. The basic model that we assume for a simplified atmosphere is known as the exponential atmosphere. This is a one-dimensional model that is parameterized solely by your altitude. And it gives the atmospheric density as some rho naught, that is a reference density associated with some reference altitude, times the exponential of negative h minus h naught over the atmospheric scale height. H is your current altitude above the reference ellipsoid, rho naught, h naught, and capital H are tabulated values that are measured from some mean atmospheric model. The scale height is defined as the fractional change in density with height. And what that means is that capital H is the increase in altitude that is required for the density to drop to 1 over the exponential. So this E is Euler's number of its initial value. We can write H as the ideal gas constant, R star, times the temperature divided by the mean molecular weight of the atmosphere times the surface gravity of the body, let's say Earth. So G naught is 9.80665 or 9.81, as we commonly approximated, meters per second squared. Here is one example of an exponential atmosphere model. This data is taken from a paper by Wirtz, 1978. The way that you would apply this equation here is you would take your current value of H, you would find which row you're in. So for example, at 65 kilometers altitude, you are in this row, your H naught value is 60, your rho naught value is 3.206 times 10 to the negative 4, and your atmospheric scale height is 7.714 kilometers. And if you plot this all together, again, plugging these values into this expression, then you get this curve. And you can see that as we go up in altitude, our density drops exponentially, such that at 1,000 kilometers, you have densities of well below 10 to the negative 13, actually below 10 to the negative 15 kilograms per meter cubed. So the atmosphere technically goes on forever, but in reality, once you are past the 200 kilometer mark or so, you're talking about incredibly small numbers. And that's why, as I said previously, 200 is kind of considered the general breakpoint, where when you're operating under 200 kilometers, you're going to see incredibly rapid deorbiting due to atmospheric drag. A few more plots from the US standard atmosphere. This is showing the same thing as in the previous slide, but now for this particular model atmosphere. And you can see that the exponential model actually tracks very well because the US standard atmosphere is inherently an exponential model, just with a few more bells and whistles attached to it. And again, you could read all the details in the full model report. This is showing both the pressure and the density plots here, and you can see that they have very, very similar curves, as you would expect from ideal gas law. And here you have a pressure scale height and a density scale height. And these are two slightly different values, but basically the pressure scale height is just creating a very similar exponential model for pressure as we did for density and defining a scale height for that.